Well, I appreciate you guys sticking around. I know it's not for me, it's for these prizes over here. That's all right. I actually have considered just talking so that you would all leave and then I'd get all of them. But I don't know if I can outlast some of you. So as Philip mentioned, my project is entitled Methodology for Smart Meter Siting and Monitoring. And the basic idea behind this is more of a micro siting rather than the macro. A couple things I'd like to say before I get started here is that my advisor is in the audience, Kirby Calvert, and he helped me throughout this whole process, offering a lot of questions and suggestions to try and get this as concise and accurate as possible. One thing I'd like to talk about too is I'm from a small utility company, and I'm sure there's a variety of sizes of companies represented here in the crowd. Small utilities do deal with different hurdles than large utilities. That might be kind of obvious, but we basically try and keep up with the large utilities, but with fewer resources. Those resources, two key resources being financial resources and human resources. So we're constantly chasing the Joneses, but with a much slower car. So the successful projects, in my experience, at a small utility are generally the result of an initial contract with a provider of software, a product, something along those lines, and then ongoing care and maintenance from a in-house manager. And those stakeholders may wear many hats, and basically they're going to determine whether the project is successful or fails. So, smart meters, as you guys may know, they're wonderful in concept. They're definitely highly, there's a lot of controversy around them. So this project won't touch at all on the controversy as far as I'm getting to like the RF radiation and everything. I have opinions on that, but that's not for here. This is really just about the communication network that is going to try and connect your office environment to your field meters. And specifically, in this case, we're looking at the steps that it takes to get either from the meter to the office or from the office back to the meter. And I'll be using the term collector meter or fixed collector quite a bit in this presentation. And basically, that's going to be your central hub of communication. I'll get into that a little bit more as we go on. So this project seeks to site those specific collector meters or collector points, kind of the intermittent data step. So overall, the project does intend to contribute to the siting and interactivity of AMI and enabling utilities to employ AMI in effective ways. Then I'm going to go into an overview of mesh networks, which are used heavily at the neighborhood level in this outlay. We'll go over the implementation and results, and then I'll have a couple conclusions. So just a quick overview, and some of this may not be all that new for you guys, but SCADA is a reality, and it's kind of the tower in at least my world of electricity. It's basically a network of devices and sensors out on the line that return information back to the field. And I say here in the slide that it provides the same information and control as if the operator's in the field, but truly it can provide a lot more. You guys have probably been around war rooms, and the ability to create computations and actually get more information out of your system than the person could actually get standing in front of the device in the field is extremely helpful. So SCADA and AMI, I see them as the two main towers of field status, and I don't think that they're necessarily mutually exclusive, but they don't necessarily accomplish the same goals, or neither do they have the same goals. And I'm trying to use the two together to bring back even more system information. I see SCADA as extremely detailed and site-specific information, and I see AMI as more of a system overview at multiple locations. It should be at thousands times more locations than your SCADA would be at. So GIS, as we all know here, is extremely important in electric utilities. It's extremely important in this too, because it's going to, in our siting project, because it's going to determine the methodology where we determine to put these collector meters to gather all the neighborhood meters. I just quickly go through this slide because I don't think I'm trying to convince anybody here about the strength of GIS. You know, obviously electric flow models, the way that we create them is based in GIS and kicked out to some sort of an engineering analysis software, and then on to, for us, an outage management software. And it's more than assessing your current situation. It's the ability to assess any planned projects, see it all in one concise view, and then also to bring in outside information, you know, not just where is this electric line compared to a gas line, but maybe we're going through a sensitive area culturally. So where I think that AMI, and I'm sorry, I didn't define AMI. I should have really defined that starting right off. AMI, for those that don't know, is Automated Meter Infrastructure. It is the way that you can communicate to your meters without physically going to see them. You can get reads from the meter. You can also then push information to the meter, be it a new program. Maybe there's a time of use program going into effect. And with outage management, there's a pinging capability that's fairly important. So once we know power is out in an area and we believe we've restored it, we can start pinging, because often there's multiple reasons for a power outage. You may be part of a large outage, but you also had a tree fall through the line in your yard. So we think we've restored power to the whole system, everything's great. You call the next day and say, hey, I'm still out of power. We would have the ability to send out a mass ping and look for return values that say, you know, these clusters or these individuals are still out of power. That's the two-way communication capability of an AMI system. 900 megahertz mesh networks are employed in this particular application, and I think they're used quite a bit in my experience in an AMI or AMR deployment. AMR is slightly different than AMI. It stands for Automated Meter Reading. The main difference is that it's a one-way communication. The meter is just pushing its information back to the central data server. So there's no ability to, there's some kind of roundabout abilities to ping or to look for meters that are out. They can send out a last gasp message that basically says, I just lost power. And so you get that. You don't have that live ability to send back a message and say, are you in power? So it's a little bit different. You also don't have the ability to push any programs to the meters in a AMR system. So a mesh network basically is exactly that. It's kind of self-explanatory in the sense that one meter may go to the neighbor's house one day, neighbor at house 2, and 2 seconds later, it may go to the neighbor's house at house 5. And it just kind of bounces through the neighborhood of meters and finds its way to the central collector meter that we're really trying to cite in this proposal. Just a quick overview of mesh networks is that they're defined by a couple key characteristics. Self-configuring nodes, that's basically what I just explained. You plug and play, no programming needed when the meter tech goes out there, pops the meter in, and it just starts finding its own route to a central collector meter or central collector fixed collector pole top. The multiple routing paths is the same concept. It can go any way that it wants to get there. Spread spectrum radios was something that was kind of new to me. It bounces within a band, a preset band of frequencies, so that because it does broadcast on ISM band for instrumentation, scientific, and medical, it's an open band, doesn't require any licensing from the FCC, so it takes another layer of red tape out of it, but it bounces around within that band so that if somebody else in the neighborhood is using that band, not only are you avoiding that interference, but you're also avoiding interference for them. So it's another self-healing aspect of mesh network. So Python is, I think it's the only programming language I know. It's very simple. I don't know if you guys have opened it up and played with it. For a guy like me, it's almost pseudocode. It calls out common commands. calls out, I can look at a code, a Python script that I have no idea what the project is, and I can understand the generalities of what the code is trying to accomplish, and I can modify it. And of course, being parameter-based, and especially this one's parameter-based, it's fairly easy. Generally, your parameters are right at the top. It's easy to hand it off to somebody and have them, with minimal expertise, be able to modify the code for their own use. So what we did here, the meat of this project, is trying to calculate meter density. And the reason we took this approach, very kind of minute, micro approach, looking at individual neighborhoods of meters, is that, again, with a small utility, our initial contract was to have one of these meter companies come in, and they tell us how great their product is, and they give us a assessment of our system based on how the RF is going to interact with each other, how the mesh networks are going to work together to get to a collector meter, and then they leave, you know. And so we're kind of left with a very coarse raster map of, you should put your meter here, and that meter, that cell may encompass 300 meters, and of course there's no subjectivity to it. There's not a, they didn't go out and look at inside that cell. One particular house may have a tin enclosure around the meter, which of course would inhibit the signal. So there's a lot of subjectivity, and we're trying to, with this, trying to take that cell, that high communication area, and look at the 300 meters within that cell and establish the best candidates so that we can basically site that meter, that collector meter, in the best spot that we can. And that's really how the whole project came about. It was in Arizona when I worked at another small utility. The metering manager came in, and if you guys have worked around small utilities, you know the personalities are a little bit different. And he was giving me guff, and he said, you know, I've been trying to get this signal from the ski area. We have a collection of meters up at the ski area, and every month we're going up there to read these meters. Manually, essentially. We're driving up there with a handheld device, collecting all the meter reads and driving back. It's about 45 minutes each way. And he jokingly said, he goes, can your stupid maps help me with that? And I said, well, maybe, you know. And so I had ArcGIS Desktop Basic. And so I immediately, and I didn't know that. And so I immediately downloaded a DEM and said, okay, let's do this. And I opened it up, and you are cheap, you don't have access to this tool. And so I said, okay. So I grab a piece of grid paper and printed off the topo at a scale that I knew, and we started doing a line of sight line drawing. And if you haven't gotten away from your computer in a while and tried to do it by hand, I encourage you not to, because it was about 10 minutes of me fumbling through, trying to do a line of sight. Embarrassingly, I used a different scale on each axis, and all told, I put it aside. I said, well, I'll get back to it. Let me figure out a different way to approach this, because I don't have a solution right now. And that's where this project basically was born. And so what we did, I want to go back one. So this is the very simplified process here. So our Python script goes in, and it'll take every meter on the system. It's a loop script. It takes that 1 meter, and it selects all for us within 1,200 feet. These signals can travel miles if they're unobstructed. We took the average distance performance of the system and decided that 1,200 feet was undershooting it, and that'd be good. So we took 1 meter, selected 1,200 feet, all meters. Took that selection set, selected out another 1,200 feet, because these meters with the mesh network have the ability to bounce through up to 16 neighboring meters to get to that one collector. The metering manager informed me that it generally hops 8 times. We call that a hop. So we calculated out to 8 hops, and then symbolized it here, and basically copied it 2 times, and then symbolized it with a ringed effect. So the first hop would be the largest, and it sits underneath the 4th and the 8th hop. And so the reason why you wouldn't necessarily only be interested in the 8th hop is because sometimes you want to see how it acts on that first hop, and then how that meter's proximity changes out to the 8th hop. So it's actually very common for a meter to be in the lowest class on the first hop, but yet in the highest class by the time you hit the 8th hop. And sometimes the logic, it's not necessarily logical how, until you look at it in a map format. So here we symbolize it, of course, green, good, red, bad, red stop, green, go, however you want to say it. And it's very obvious here on this Cape George area that's very dense. Any of those are going to pick up all the neighboring meters. But what I'm really looking for is something outside of the dense area that has a green dot in the middle as a center point. And that to me says that I'm in the highest class. I can see 885 meters around me by the 8th hop, and I'm on the edge of a dense area, and I'm close to another dense area. So if you were to just drive out there, kind of windshield view, you may choose to put a meter right here, dead center of all this green, and that's great. But we know the capacity of the meters can pick up more than just this green area. So we can put it on the outskirts of this dense area and possibly take up this dense area also. So it's a little bit, in my mind, illogical in that sense until you see it displayed spatially, that I'm trying to get all these reads from the dense area here and then all these reads from this dense area over here. And of course this map is completely interactive, and the metering manager can come in and look at not only the characteristics results from the Python script, but also can look at the normal electric categories, the meter number, the meter type, the meter phasing, those kind of things. Because you don't generally want to put one of these meters at a 3-phase meter. These are a simple meter, so you kind of want to keep it just on a regular residential home. And we could easily exclude those, but we want those 3-phase meters to participate in the proximity also. So the second aspect of the project that I actually think is more useful in an ongoing sense is the system monitoring. So each morning, a metering manager or an interested party can come in and see how the system communicated the day before. And it's actually extremely simple. It's just a SQL query that we run every night, and we're pulling from the meter database the meter IDs and then the collector ID. So there's thousands of meter IDs, and then there may only be 100 collector IDs. And we're going to pull that over into the GIS database and symbolize based on the collector ID. So you end up with a result such as this, where we can color that all the green is going to one collector, blue to the other. And most importantly for that is the starred areas. Those are null. So that means they're not communicating at all. And more than likely, a quality metering system is going to be able to give you some sort of alert or tabular reference that, hey, this meter has dropped off and it's not communicating back. This aspect of the project would allow the manager to go, great, meter 4, 5, 6, 7, 8, 9 is not communicating. Where is it? That's what I'm interested in. So they can go to the map, look at the geographic location, figure out if maybe we removed that meter and just didn't take it out of the system, or maybe we need to move a collector closer or hit an intermediary, set up a repeater somehow to get that signal back. So that's a really simple aspect to help visualize the ongoing system performance. So the results of this project were a complete methodology for the localized siting of AMI meters, and it is a functional and transferable Python script, just a couple parameters so that you could take it to your organization and run your calculation pretty quickly depending on the size of the data set. I do have the map document, and that's minimal local customization. I find with GIS users, though, they'd probably go, oh, that's great, throw it away, and I'm going to make my own because I got my own personality. Also a network map for creating those nightly SQL pulls, which we call NyQuil pulls. And a simple web-based map viewer. As you probably all noticed, that's ArcGIS Online. It began in Flex, and I didn't realize how much Flex was kind of hated until this week. I mean, I knew I hated it, but it drove me nuts trying to get that first Flex map, and then the second one was actually pretty easy, but the first one. God, it took me a week. So in conclusion, I hope that this project does contribute to the installation, monitoring, and planning of AMI or AMR networks. I think that's important that even though the two kind of projects would be different from each other in their end result, the communication and the siting of that communication is identical. You have to have that localized connection. Definitely the daily tool for metering managers, visualization, and communication, and the concepts also apply to non-electric and completely outside of the utility industry. Really, when you're dealing with just a simple proximity script, I believe that the applications are across industry. And again, moderate expertise needed to follow this. If I can do it, I think anybody can do it. The other thing I wanted to mention, I have to kind of expose myself as a thief. So I'm here to steal from all of you. And I don't mean that just like look the other way and I'm going to grab these or the Woolpert stuff that I stuffed in my bag last night. I think that the communities are all about sharing information, and for most of my career I've just kind of been a one-way, like bring it in, I'll take that. And so I do hope that I'm kind of maybe going to be able to give something back to the community that somebody might find an application for within AMI, within AMR, or even outside of it. And with that, I'd just like to especially thank all of you guys for sticking around. I know it's the gifts, not me. And want to thank Kirby Calvert for being here. Thank Penn State. Thank Mr. Mark Limbrower for putting this on, and Range Resources. And most of all, Matt Chase, who was the cocky meter manager that came in and got me going on this. So open it up to any questions if anybody has one. Well, that's easy. Go ahead.
Yeah, so you mentioned that this works really well for mesh networks, that you're describing with the network queries. Would it work for a network that wasn't a mesh network? Are all utility?
Yeah, I hadn't really thought about that, but the aspect that I'm trying to cite really has nothing to do with the mesh network. I hadn't thought about that until right now. The mesh network operates on its own and finds its own way. It's really the second tier of communication that I'm trying to cite. So there's the mesh network works at the neighborhood level, and then it relays its information up to the collector meter. And then that relays back to the central data server that might be through, we would prefer fiber, but you can't have fiber everywhere. So you may have radio or cellular. We've been using cellular in a lot of spots. And so that aspect is really just more the, it's just how to relay from that one central meter back to the central data server. The mesh network aspect is really, takes care of itself. We're just trying to put one collector in a good spot that has the greatest potential to see the neighborhood meters there. You have a question?
Thank you.
Okay. Gifts time? Thank you. I appreciate you guys listening.